Welcome to the third and final paper of Edexcel's November series GCSE higher tier maths exams. So we've had paper 1 and paper 2. This is the final calculator paper, and I've got to say the last question on this paper, I've seldom seen a more awkward GCSE question. I think it's so hard to know what to do with it. Once you know what to do, it's not so hard, but getting started with this one I thought was an absolute mystery. So if you managed question 23 and you got it yourself, then my hat's off to you, sincerely, I mean that. Anyway, question 23 is at the end. Let's just start from the beginning, quite naturally and logically. Let's have a look, before we get carried away, at question number 1. Question 1, we have a scatter graph showing information about the volume of traffic and the carbon monoxide level at a point on a road each day for 22 days. One point is an outlier. Write down the coordinates of this point. So, an outlier is just a fancy mathematical word for just a point that doesn't actually happen to fit the general pattern. So it's just a bit of a freak result. It doesn't fit the general trend. So you can see here, hopefully, these points here are all going in a generally positive direction, whereas this one here just seems way out. So the outlier is actually this point up there. So the coordinates of this point are 100 and 18. So there's the first marks to getting the coordinates of that outlier. Then for part B, on another day, 370 cars pass this point on the road. Estimate the carbon monoxide level for this day. I do say to my students, only half jokingly, whenever you see a scatter graph, be thinking of a line of best fit. A line of best fit is designed to go close to the trend where the points seem to be following. As a general rule of thumb, you want to have roughly the same number of points below your line of best fit as above it, and don't go out of your way trying to chase outliers. So ignore this point altogether and try and get a straight line going through or close to most of these points. This was my guess for it. So we estimate the carbon monoxide using the line of best fit. This is mine. And you need your line of best fit to pick up a mark. I won't award you a mark if you're not using line of best fit. The examiners might be more generous, but not me. Anyway, line of best fit is what's needed. So now what we do is we use the line of best fit and we read off this value of 370 cars. So 370 is here, so we go up and along and read off what the carbon monoxide level would be as an estimate for those number of cars. So 370 cars comes to this point here. If we read along, you should see it comes to about 14. So my estimate, based on my line of best fit, is 14 milligrams per cubic metre. And by the way, because line of best fits vary, yours will be different to mine, a valid range for part B is anywhere between 12.8 to 14.6, but it has to be based from a correct method of reading your line of best fit. So 12.8 to 14.6 is valid for full marks, but you need to show evidence of using a line of best fit and reading off your line of best fit to get a value in between these two. Alfie says, because there is an outlier, there's no correlation. Is he correct? You must give a reason for your answer. Well, if I just go back for a second, we can see here it clearly is a pattern. There's a trend. That's what correlation is. Generally speaking, as the volume of traffic increases, the carbon monoxide increases. That is the general trend. But often there are exceptions to general rules. This is an exception to the general rule. But generally, there can be correlation, even if there is an outlier, or even outliers plural. So to return to Alfie, he's not correct, and we need to just explain why. So something like no, he's not correct. It's always possible that there is correlation, but that some point or points are exceptions to the general rule. Question 2. Natalie's making potato cakes in a restaurant. She mixes potato, cheese and onion so that the ratio of weight of potato to the weight of cheese to the weight of onion is 9 to 2 to 1. So you can get this into a ratio table now. So 9, 2 and 1 for potato, cheese and onion, and 9 lots of potato, 2 lots of cheese, 1 lot of onion gives us a total of 12 parts, 12 lots or 12 measures of the ingredients. But she's just not making 12 lots. How much is she making to be exact? Well, she's making 600 grams of potato cakes. So her 12 measures of all these ingredients must total to at least 6,000. Assuming she's not going to make any waste, that 12 lots needs to total 6,000 grams. So if that's the case, and 12 lots equals 6,000 grams, how can we calculate what just one lot is worth? Well, we can do 6,000 divided by 12 to work that one out. So 6,000 divided by 12, that gives us 500. So in other words, what we need to do to go from this line to the final line, where we can actually deduce how many grams these ratio parts represent, we can multiply all of these values by 500. So we've already times that one by 500. We now need to do the same for the 9, the 2, and the 1. 9 times 500 gives 4,500. 2 times 500 is 1,000 grams. An onion, 1 times 500, 500 grams, about a pound of onions. A pound in terms of weight, not in terms of price. So, we're talking here about cheese. So cheese costs £2.25 for 175 grams, and we need to work out the cost of cheese needed to make her potato cakes. So £2.25 for 175 grams, but she needs 1,000 grams of cheese, so obviously it's going to cost her more than £2.25. But we can start from this and scale it until we get to 1,000 grams worth. So £2.25 is 175 grams. What we could do here is work out what just 1 gram's worth by dividing both sides by 175. So £2.25 divided by 175, 0.01, so 1 penny and a bit, so 0.01285714. A fairly awkward number, which I'll just leave there on my calculator, ready to use again. So this one here, get this awkward number, that must be what it is worth for 1 gram, about a penny per gram. Then to go from 1 gram to 1,000 grams, we can finally multiply both sides of this by 1,000. So the cost of 1,000 grams, the cost of the cheese which she actually needs to pay for, is this number times 1,000. Press SROD, and we get £12.85, but that 5 is next to a 7, so it actually rounds up to 6. So to the nearest penny, £12.86 is the cost of cheese needed for her potato cakes. That's the answer, therefore, we've put down. Question 3, standard form. So part A, work out 4.5 times 10 to the 5 as an ordinary number. We can simply type this on a calculator. So 4.5 times 10, just typing exactly as it looks here, press the power button, then press 5, press equals 45 with 4 zeros after it. That's our answer, therefore, for part A, 450000. Part B, write 0.007 in standard form. You can get your calculator to do this. If it's a small number, 0. something, it's always going to be times 10 to the power minus. There's going to be a minus power of 10, and you can work out what the negative power of 10 is by counting how many leading zeros there are. We've got 1, 2, 3, so therefore it's going to be minus 3. And where do we put the decimal in this number? So it's between 1 and 10. We put it after the 7, so it's just simply 7. 7 times 10 cubed. So that's part A, that was part B, finally part C. Work out 4.2 times 10 cubed plus 5.3 times 10 squared. Give your answer in standard form. So again, just typing it in exactly as it looks, not trying to do anything complicated or fancy. 4.2 times 10 to the power 3, then plus 5.3 multiplied by 10, power button, squared. We get 4,730. So first step, just write down, is 4,730. That's not in standard form, of course. For it to be in standard form, the decimal needs to be in between the 4 and the 7, because 4.7 is therefore in between 1 and 10, which is where it needs to be. So it's 4.7 multiplied by 10 to a certain power. 4,730 actually has its decimal at the end of that 0. To work out our power of 10 we need, we work out how many digits are in between where the decimal actually is and where the decimal would have needed to go to make the number in between 1 and 10. You can see here that there's 1, 2, 3 digits in between, so we need to put 4.7 times 10 cubed. Question 4. A water tank is empty and Neil needs to fill the tank with 2,400 litres of water. Company A supplies water at a rate of 8 litres in 1 minute 40 seconds. Company B supplies water at a rate of 2.2 gallons per minute. So Company A would take more time to fill the tank than Company B would. How much more time? So this is a comparison question. Think about Company A in a separate area on your paper, Company B in a separate area on your paper. Maybe divide your page into left and right sides. So Company A, 8 litres in 1 minute 40 seconds. Company B, 2.2 gallons per minute. Let's make a Company A and Company B separately. So first of all, Company A, we've got 8 litres in 1 minute 40 seconds. So obviously we've not just got 8 litres though to fill, we've got 2,400 litres. So to go from 8 up to 2,400, we need to multiply it up some. How many 8s go into 2,400? That's what we find what to multiply by. 2,400 divided by 8 is 300. So what I need to do here, I need to multiply the 8 by 300 and the 1 minute 40 by 300. So 1 minute 40 multiplied by 300. There's a few ways of doing this. What I consider is thinking of it in terms of seconds. 1 minute is 60 seconds, plus another 40 seconds gives us 100 seconds. We can then times that by 300, which gives us 30,000 seconds. Another way, is I've put it here in terms of minutes, you could have just did it straight in minutes as well if you wanted. Going back to what I've got here, that's what we've got in terms of seconds. To go back to minutes, because we've got 60 seconds in each minute, we could divide by 60. We get 500. Now, to have got it in terms of minutes straight away, there's two things we could have done. We could have used this mixed number function on the calculator. Press Shift and the fraction button. 1 minute and 40/60ths of an extra minute multiplied by 300 gets us to where we need. And also these buttons here are essentially used for hours, minutes and seconds. So if we type in 0 hours, 1 minute, so 1, press again, then 40, press again for the minutes, then multiply that by 300, we get 8 hours, 20 minutes, which again you could convert into minutes. 8 times 60 is 480 minutes, plus 20 is 500. So I've talked your heads off about how you can use time functions on your calculator. Anyway, 2,400 litres in 500 minutes. That's what Company A is, 500 minutes to wait. Company B now, 2.2 gallons in 1 minute. Now we're told how many litres makes a gallon. 1 gallon is 4.54 litres. So I can change this into litres by multiplying it by 4.54. And that gives 9.988 litres in 1 minute. So I need to go from 9.988 litres up to 2,400. What I could do first is divide both bits of this relation by 9.988 to work out what 1 litre would take. So dividing by 9.988, so 1 divided by 9.988 gives us 0.10012 and so on and so on. So 1 litre would take about a tenth of a minute to fill. So a tenth of a minute to fill a litre using Company B. Then to go from 1 litre to 2,400, I can now multiply both sides by 2,400. So take this number here, multiply by 2,400, gives me 240.29 minutes. 0.28, 0.29, I didn't round off essentially properly. But 2,400 litres is about 4 hours to fill up. So clearly, Company A takes more time. 500 is more time than 240. How much more time? We can now just do 500 take away 240.28. So 500 take away that one given answers in terms of minutes, correct to the nearest minute, 259.7, that's closer to 260. So our answer to the nearest minute is 260 minutes. In terms of the calculations, that's what we'd do. 500 take away 240.28, blah blah blah, 260 to the nearest minute. Question 5, we've got the first 4 terms of a Fibonacci sequence. So first of all, what on earth is a Fibonacci sequence? We need to remember. Well, a Fibonacci sequence is a sequence of values in which, after the first 2 terms at least, one term is the sum of the previous 2 terms that went before it. So you just need any 2 terms to get going. If you look at this term 3a, that's the sum of the 2a and the a before it. 5a is the sum of the 3a and the 2a before that as well. So we could actually carry on and say that this must be 8a, because 8 is 5 plus the 3 before it. We're now told the sum of the first 5 terms is 228. So this one, plus that one, plus that, plus that, plus that, needs to add up to 228. So this is now actually a very simple equation to solve. A plus 2a is 3a, plus another 3a is 6a, plus 5a is 11a, plus 8a is 19a. So we've got 19a equals 228. Therefore, if we divide both sides by 19, a is 228 divided by 19, which gives us an answer of 12. This all hinges on knowing what a Fibonacci sequence is. Question 6. In a bag there are only red, blue, green and pink counters. A counter's going to be taken at random from the bag, and the table shows a probability of taking a red counter or a blue one. Green and pink haven't been filled in yet. But the probability of taking a green counter is 0.2 higher than the probability of taking a pink one. And this is our clue and how we're going to get started. So if I say taking a pink one is, say, P, I call that P, then the chance of taking a green one is 0.2 more. 0.2 more than P is P plus 0.2. I can now generate an equation in terms of P and solve. So if I'm picking a counter, it's got to be either red or blue or green or pink. When I add all these probabilities up, it's got to add up to 1. So 0.05 plus 0.15 plus P plus 0.2 plus P equals 1. We can now simplify this. P plus P gives 2P overall. 0.05 plus 0.15 plus 0.2 gives 0.4. So 0.4 plus 2P equals 1. If I now take away 0.4 from both sides, then 2P must be 0.6. Finally, halving both sides to get what 1P is, P must therefore be 0.3. So we can replace P and P plus 0.2 with 0.3 and 0.5. Like so, and that's our table properly filled in. Green 0.5 and pink 0.3. For part B, we're told that there's 18 blue counters in the bag, but the probability of picking a blue counter is 0.15. So what this means here is that actually the 18 blue counters, because there's a 0.15 chance of picking them, 18 must be 15% of the counters. So 18 counters is 15% of the total. We can now scale from 15% up to what 100% is to get the total number of counters. So I could work out what 1% is by dividing both sides of this by 15. So if I do that, 18 divided by 15 is 1.2. So 1.2 counters would be 1% of them. Finally, to go from 1% to 100, I can now multiply both bits by 100. 1.2 times 100 is 120. Therefore, in total, there must have been 120 counters in this bag. Question 7, we have a diagram which is a segment of a circle and a right-angled triangle. So in total this makes a sector, centre 0 and radius 8. So we need to work out the shaded segment PQR, giving our answer correct to 3 significant figures. So we need to think of this shape in terms of split up into a separate triangle and this segment. So if I colour this triangle in yellow, then I can say that this PQR must be this whole sector, including the curved bit, minus off this triangle colour-coded in yellow. So if that's a right angle, how much of a circle is this? Well, hopefully you can see that's a 90-degree angle, and a full circle's got 360 degrees. This has to be a quarter of a circle. So the shaded area is the area of this quarter circle. So the area of a circle is pi times radius squared. So this would be pi times 8 squared. But because it's a quarter of it, we need to divide that by 4. And this one here, area of a rectangle, is half times base times height. It's also going to be half times 8 times 8, or 8 times 8 divided by 2. So we can now type in this on the calculator to get what it's actually worth as an area. So shift pi times 8 squared all over 4, and minus away from that 8 times 8 all over 2. That gives us, correct to 3 significant figures, 18.3, because that 2's next door to a 6, so rounds up. So the area of that shaded region, therefore, has to be 18.3 centimetres squared. Question 8 is about recognising graphs of proportionality. So part A, using the axes below, sketch a graph to represent the statement y is directly proportional to x. Well, if one thing is directly proportional to another, whether it be y directly proportional to x, A being directly proportional to B, whatever, a graph of one against the other will always have to be a straight line going through the origin. Not a straight line cutting the y-axis here or the x-axis. It has to go through the origin and has to be a straight line. So something like this would get you the marks. Any straight line could be steeper, could be less steep. As long as it goes through the origin, that's absolutely fine. For part B, if y is inversely proportional to x, it's anything but a straight line. It's a curve which hugs the y-axis and the x-axis, but never ever dares to quite touch. So as it gets closer to the y-axis, it goes steeper and steeper and steeper. It gets closer and closer, but never touches. And the same with x as well. It looks almost like a quarter circle, like the bottom left of a circle, something like that. So the curve you need to draw will be something a little like that. Question 9. On Monday, 12 people took 5 hours to clean a number of cars, it says. So, what to do here? Let's imagine all these people at work. So imagine 12 people, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of them cleaning a number of cars. I don't know how many cars there are. I've made up with 6. It doesn't really matter. But all these 12 people have worked for 5 hours each. So in total, how much work is that in total for just one person? If you've got 12 people working 5 hours each, that's a total of 12 times 5, which is 60 hours worth of work. So they've shared it equally, you'd hope if it's a fair workplace, they've shared it equally between themselves. So 60 hours of work divided by 12 people is 5 hours each, as obviously it is, because we're told that. So for part A, we need to use this assumption that they worked at the same rate to work out how many hours 15 people would take to clean the cars. So if there's still the same number of cars, then it'll still be 60 hours worth of work. But rather than sharing that 60 hours between 12 people, now we're sharing the 60 hours worth of work between 15 people. So the calculation now would be 60 divided by 15 for these 15 people, which would be 4 hours worth of work. Now, for part B, it says this assumption is wrong. We assumed that all people worked at the same rate. So because the assumption is wrong, how might this affect the time taken for 15 people to clean the cars? I do think this is quite a foolish question. It doesn't say if the assumption is wrong in terms of some people work faster or slower. It just says it's wrong. So because the assumption is wrong, the time taken could be affected either on the high side or the low side. It could be affected in either direction because you're not told any information really. So all we need to get to pick up the mark is something like this. Essentially, it could actually take them more time than 4 hours, or it could take them less. For example, if these 15 people are trainees, it might take them less. So part B, You can always put anything for an answer, really. It just seems like a bizarre part B to me, but hey, what do I know? Question 10. The diagram shows two right-angled triangles, ACB and DEB. The key insight here is that these two triangles are similar. So BED is just BCA shrunken down. Or you can imagine that ABC, the large one, is an enlargement of BDE, with the centre of enlargement being at point D. They've got the same angles, so they are all similar. So next, what we need to do is to think of ACB separate to just DEB. So we've copied out the same diagram, we're just thinking of a large triangle now. So let's label on these dimensions. So AD is 9, so I can label this 9. From D to E is 2, so I can label this on as well. And then from D to B is 6, so finally labelling this on as well. We now need to calculate the length of C to B. But if you notice here, from A to D, then from D to B, is the same as all the way from A to B. So from A to D is 9, then an extra 6 to B. That means that from A to B must be 15. 9 plus 6 gives 15. So now we can think about DEB, this small triangle, in relation to the larger one. So the hypotenuse on DEB is 6, whereas for ABC, for the overall larger triangle, the hypotenuse is 15. So we've gone from 6 to 15. So what must be the scale factor of enlargement to go from 6 centimetres up to 15 centimetres? Well, we can do one value divided by the other to find out. 15 centimetres divided by 6 gives us 2.5. So what we found out here is that triangle ABC is an enlargement of triangle DEB, scale factor 2.5. So because of that, this yellow triangle ACB is this green one blown up by scale factor 2.5. We can now, knowing this, work outside A to C. So to go from D to B to AB, we multiplied 6 by 2.5. So to work out AC, we take this corresponding side here, D to E, which is 2, and multiply that by 2.5 too, and 2 multiplied by 2.5 gives us 5. So now, just going back to what we actually want to find out, we want to find the length of CB. We want to find this length here from C to B at the bottom. So now, after all this similarity of triangles, we've actually now got a Pythagoras question hidden within. We know this side is 5, we know the hypotenuse is 15, we know ABC is a right-angled triangle, and we need to find from C to B, which is one of the shorter sides. So all we've got now is this essentially. So using Pythagoras, 5 squared plus x squared equals 15 squared. So 5 squared is 25, and 15 squared is 225, so we can fill in those details now. Then if we arrange this equation in order to solve it, we can subtract 25 from both sides to get x squared is equal to 200. Then the final step, just square root both sides of this, so square root of 200, press equals, and press the S arrow D button, and then read the question carefully. We need it to 2 decimal places. So we need to keep the 1 and the 4. That 4 doesn't round up because it's only next to a 2. So our final answer is 14.14 centimetres. Question 11. Freya writes down the value of x correct to 1 decimal place. She writes down x is 6.4. Just imagine for a second the very, very boring 1 decimal place times table. Not 1, 2, 3, 4, 5, 6, but 0.1, 0.2, 0.3, 0.4, and so on and so on and so on, until we get to within the neighbourhood of 6.4. So we'd eventually come to a section of a number line like this. 6.0, 6.1, 6.2, and so on, with 6.4 being our value, the original number must have been closer to before it was rounded. So it's closer to 6.4 to 1 decimal place than to 6.3 or 6.5. So it stands to reason that whatever this number was before it was rounded must be to the right-hand side of this marker, otherwise it would have gone to 6.3, and the number must have been to the left-hand side of this halfway point in between 6.4 and 6.5. If it were on the right-hand side, it would have rounded to 6.5. So our boundaries for what the number must have been originally must be in between here and in between here, like so. Now this one is bang in between 6.3 and 6.4. Imagine it being £6.30 and that being £6.40. Halfway in between £6.30 and £6.40 would be £6.35. And x needs to be in between £6.35. In the same way, halfway in between £6.40 and £6.50, this higher boundary would be 6.45. These two values then fill in our error interval, 1 mark for each. So x needs to be at least 6.35, but x must be less than 6.45. 1 mark here, 1 mark there, 2 marks in total. Question 12. ax6 to the power 1 over n equals 7x cubed. Work out the value of a and the value of n. So, ax to the 6 to the power 1 over n. If we've got something in brackets raised to a power, then everything within these brackets is given to this power. So we raise a to the power 1 over n, and we do x to the 6 to the power 1 over n as well. So a to the 1 over n we can leave as it is. Now if we've got a power next to a power, to work out a power of a power, we multiply the powers together. So 6 times 1 over n gives us as an overall power 6 over n, like so. And we're told that that's equal to 7x cubed. So now we can just compare the powers. So 7 must be the same as a to the 1 over n, and also x to the 6 over n must be the same as x cubed. So I don't know a or n, so that's no use to me. But this other one here is. I don't know what x is, but just focusing on the powers, I've got one side is equal to the other. So what I can say is that this power 6 over n must be the same as 3. So therefore 6 divided by n equals 3. What number, if I divide 6 into it, gives me 3? 6 divided by 2 works. So therefore n equals 2. Based off that, we can then substitute back that n equals 2 into this expression here. So a to the 1 over n means a to the power a half. Now something to the power half is the same thing as the square root of that value. So a to the half is the same as the square root of a. So the square root of a, which is a to the half, equals 7. So therefore, if we square both sides, a must be equal to 49. A is 49 and n is 2. Question 13. A pattern's made from 4 identical rectangles like so. The sides of the rectangles are parallel to the axes. Point A has coordinates 3, 4, which has been labelled. Point B has coordinates 11 and 20, that's been labelled as well. And point C is marked on the diagram here. We have to find the coordinates of C, showing all your working. So this might be a nightmare to start off from. But just think about how long is each rectangle, how wide is it, and build it up in terms of algebra, actually. It's not so much coordinates, this is almost like a geometry and algebra puzzle. So, what I mean by this is let's call W the width of each rectangle and L the length of each one of these rectangles. Because these rectangles are identical, each W will be the same and each L will be the same. So let's think about as we move from A to B. A is 3 and B, the x-coordinate, is 11. So from 3 to 11, this distance here has to be 8 units. So in terms of widths and lengths, how could I go from A all the way along to where this dotted line at B is? Well, I could go along here, which is a length of this bottom rectangle. So I could do the length, but it takes me to this point. Then from this point to there is all I need to go. Now from here to there is almost a full length, but it's just missing out this bit here. So it's this full length apart from this here, which is a width. So this section here, which I need extra, is the length without the width. That's L minus W. So in total, from this point to that point is L plus L minus W. L plus L is 2 L's. So overall, as a simplified expression, from A to B going horizontally is 2L minus W. We can therefore say that 2L minus W equals 8, because A is 3 and B is 11. 11 take away 3 is 8 units. So 2L minus W has to be equal to 8 units. We can then do the same idea exactly, but thinking about going vertically. So vertically, A is 4 units for Y, B is 20 units for Y. So from A going up to B is 16 units. So we can do this by going up here, which is a width. That takes us up to this point. But this step is a length. So width plus a length takes us to here. Then one final step more is an extra length. So width plus length gives us W plus 2L, or 2L plus W. And because that takes us from winding 4 to Y equals 20, 2L plus W must give us 16. We now actually have a pair of simultaneous equations to solve. So if we add these together, because the W's are the same, but got different signs in front of them. So if we add them, what will happen is minus W plus W will cancel and will eliminate. So we'll have no W's at all. 2L plus 2L, though, gives us 4L. The W's cancel. 8 plus 16 is 24. Therefore, dividing by 4, L must be 6. Now we know that L is 6, we can substitute it back into one of these equations here. So if L is 6, I can put it into, let's go for this bottom one here. 2 times L means 2 times 6 plus W equals 16. 2 times 6 is obviously 12. So 12 plus W equals 16. Therefore, of course, W must be 4, because 12 plus 4 gives us 16. So in terms of that working coordinate C, so C is here. I start at 3, 4. So what I need to do to get to C is add a length onto my Y coordinate. So the length is 6, so I add 6. Well, I don't know, I've put multiply. Must be rather tired, I don't know. So add 6 that way. And then to go from A to C vertically, we're adding an extra width. So the width is 4, so therefore we add on 4 in the vertical direction. So piecing all this together, the x-coordinate was 3, we've added 6 to it. The x-coordinate at C, therefore, now is 3 plus 6, which is 9. And the y-coordinate started off being 4. We're now adding on an extra 4 to it. 4 plus 4 gives us 8. So C, therefore, must be 9 and 8. Question 14. Oliver and Jessica have Oliver and Jessica have in total half as many sweets as Fran and Gary have in total. So Fran and Gary share their sweets in the ratio 2 to 3. And then Olivia and Jessica share theirs out in the ratio 9 to 1. I think Olivia's being slightly unfair there, but I don't know the background to the story. So let's think of 2 ratio tables, one for Fran and Gary, and the other for Olivia and Jessica. So we can fill in these ratios. Fran and Gary, 2 lots to 3 lots, and similar for Olivia and Jessica. Then filling in those totals, 2 lots plus 3 lots is 5 lots for Fran and Gary, and 10 lots for Olivia and Jessica. But just returning to the beginning of the question now, it said clearly that Olivia and Jessica have in total half as many sweets as Fran and Gary have in total. Olivia and Jessica have 10 lots in total, and that's meant to be half of what Fran and Gary have, but Fran and Gary have 5 lots. So if 10 is half of what Fran and Gary have, then Fran and Gary should have 20 really, because then 10 is at least half of 20. So let's scale Fran and Gary's up to 20 lots, then half of 20 lots will be 10 lots, and then the ratios are consistent. So how to go from 5 lots to 20? What would I multiply by? Clearly, we'd have to multiply by 4. Therefore, to keep these other numbers in the ratio balanced, I multiply the 2 by 4 and the 3 by 4 as well. So 2 times 4 is 8, 3 times 4 is 12. We've now got a total of 20 parts. Because we need Olivia and Jessica to have half, we'll leave those as they are at 10 parts, so we're not going to move that on at all. Just keep these numbers exactly as they are. So Fran's got W, Gary's got X, Olivia's got Y, Jessica's got Z. W, X, Y and Z. I've already put them in the correct order. So as a ratio we want W, X, Y, Z, which is Fran, Gary, Olivia, Jessica. So we've got these numbers already. Fran is 8, Gary's 12, Olivia's 9, and Jessica's 1. So as a ratio of 4 numbers, it's 8 to 12 to 9 to 1. And that's all we need to do. That's question 14 done. Question 15, we have a graph given the volume of water in litres in a container at time t seconds after the water started to flow out of a container. So maybe this container is leaking or it's draining water and it's meant to, who knows? Who cares? Anyway, using the graph, work out an estimate for the rate at which the water is flowing out of a container when t equals 12. You must show you're working. Well, a rate means in terms of a unit of time, so per seconds or per hours or something like this. For example, speed is a rate of covering distance. So we need to be dividing by a unit of time. So in other words, what we're going to need here is something to do with dividing by time. So if you notice here, time is on the horizontal axis, so a change in something horizontal, if we divide by t, that might give us a rate. So actually the clue here is we might need to draw a tangent to this curve. If we did litres divided by seconds, y divided by x units, litres per second, that is a unit of a rate of drainage. So we need to do a tangent at the point when we've got t equal to 12. That's the key thing to start off with. So the tangent is a straight line that just touches the curve when t equals 12. It doesn't slice it one way or the other, it just scrapes off the edge. So t equals 12 is there, and so our tangent needs to come in like this. It's going to have a negative gradient just touching there, then bouncing back off. Something like this. Now for GCSE, it's not an exact science. It is, when you come to A level, you can work out tangents exactly. But for now, is it like this? Is it slightly steeper, slightly narrower, slightly less shallow? I don't know. But actually, the examiner gives you what's known as tolerance if you're plus or minus a few points out from what they think it should be. So as long as you're fairly close to having the right gradient from your tangent, you should be fine. We'll mention that at the end of the question as well. Now we've drawn the tangent, we need to pick 2 points on the tangent that we can work out the gradient from. So my 2 points will likely be different from your 2 points, and that's fine. But the 2 points I'm picking are these two here. So this point is when t is 5 and the volume is 23, and that one here is where the time is 30 seconds and the volume is 1 litre. So just label along these points clearly. We can now work out the gradient of that red tangent by working out the change in y divided by the change in x. And because we want the rate at which the water is flowing out, we don't need to worry if it's a negative gradient, just think about the size of the number. So the rate is the change in the y direction, the litres, divided by the change in the x direction, which is the time. So the litres goes from 23 litres down to 1, and the time goes from 5 seconds up to 30, so that's a 25-second gap. So 22 litres in 25 seconds, 22 divided by 25, that gives us our rate. So as a decimal, press S arrow D, it's 0.88 litres per second. So that's the answer we put down. Now, if you've got a different value to that because you expect a different gradient, that's absolutely fine. If you're thinking, well, is my answer okay? Will that get a mark? What you need here, from your gradient being drawn on at the proper place, you need your tangent's gradient to be somewhere in between minus 1.0 and minus 0.7, so that the rate you get is between 0.7 and 1.0. But it needs to be based off you drawing a tangent at the right place and having a valid attempt at actually drawing on the tangent. So you need to know what a tangent is. You can't just guess a number in between 0.7 and 1 and get your marks that way. Question 16, we've got a curve which has equation y equals x squared plus 3x minus 3, and then we have a line with equation y minus 5x plus 4 equals 0. Show algebraically that C and L have exactly and only one point in common. Well, C and L will intersect, will cross over, when the graphs meet. So that's when x squared plus 3x minus 3, which is the equation for y in terms of C, we can then make y the subject for equation L. So if we add 5x to both sides, for starters, we then get y plus 4 equals 5x. And finally, if we take away 4 from both sides of this equation, then for line L, we get that its equation is y equals 5x minus 4. So the lines intersect and have points in common where one value of y, for curve C, is equal to the other value of y, for straight line L. So we're going to meet when this equation, or this expression, is equal to the other. So essentially now we're solving a quadratic. So when solving a quadratic, it's always best to have it all on one side equal to 0. So if I take away 5x from both sides, first of all, the left will then become x squared minus 2x minus 3 equals minus 4. Then finally, if I add 4 to both sides, I then get that x squared minus 2x, but then minus 3 plus 4 gives us plus 1 equals 0. Now this will now factorise as well. So I need to find two numbers that multiply together to give me 1, but when I add them together I get minus 2. So the numbers that work there, the only numbers, are minus 1 and minus 1. Minus 1 multiplied by minus 1 is positive 1, and minus 1 added to minus 1 is the same as minus 1 minus another 1, which is minus 2. So it becomes x minus 1 equals 0. In other words, x minus 1 squared equals 0, and therefore x equals 1. So in other words, there is therefore only one point of intersection between, now what are they called, C and L, and that's when x is minus 1. Nothing else to say. That's all there is to that one. You could work out the coordinate of y as well, but it's sufficient to just show that where they're equal to each other gives a perfect square with only one solution. Because it goes into x minus 1 and that bracket is duplicated, that shows us only and exactly one solution for where they meet. In other words, they have 1 point in common. Question 17, we've got that y is directly proportional to the square of y. So, sorry, x is directly proportional to the square of y. So x directly proportional to y squared. That's what the first bit means algebraically. So this symbol here looks like a fish. You don't solve equations using a fish. Let's get rid of a fish, put it in the oven or something like this. We replace the fish with an equal symbol, and then if it's directly proportional, we say it's k multiplied by whatever came after the fish. So x equals k times y squared, where k is some constant to be found. So that's how we get this expression here. The next one is that y is directly proportional to the cube of z. So that means that y is directly proportional to z cubed. So in the same way as before, we can replace the fish with an equals sign. So we say y equals. We replace the fish with an equals, and then we take some letter, which is a constant, and multiply by whatever came after the fish. So we can't say k times z cubed, because k has already been used for the constant for this one here. So let's use a different letter. Let's just call it maybe L. So y equals L times z cubed. So all I'm saying here are k and L are just some constants, just numbers which don't change. Now, what we want here, though, is a formula for x in terms of z. We don't want to have y at all in this. So we could eliminate y and replace the letter y with what y is in terms of z. So from this one here, where y was directly proportional to the cube of z, we got this expression here, that y equaled L times z cubed. So what we could do is we can actually substitute this expression for y into the top equation. So we can substitute in like so. So then what we're going to get, once we substitute it in, is x equals k y squared, then y is L times z cubed, so that's the same as k times L z cubed squared, just using the fact that y is Lz cubed. Now there's a bit of neatening up to do here. So x equals k. Now Lz cubed is all being squared, so we need to square the L, so we get L squared, and then we get z cubed squared as well. So z cubed squared means z cubed multiplied by z cubed, which gives us z to the power 6. So therefore we get that x equals k times L squared times z to the 6. Now k and L were just constants. So whatever k was, it's just a number. Whatever L is, it's just a number. So k times L just means some number times another number. So kl squared is just going to be another number as well. So I'm just going to say x equals big N, some big number, times by z to the 6. So I'm just replacing here. Whatever kl squared is, I'm just calling it big N, because I can't be bothered writing down kl squared all the time. That's just another number, call it big N. Now we're nearly home and dry. So now we can relate z in terms of x. We're told that z is 2 when x is 32. So substituting these values in, you get 32 equals n multiplied by z to the 6, which is 2 to the 6. 2 to the power 6 is 64, so 32 equals 64 times n. Therefore, dividing both sides by 64, we can then find out what our value of n actually is. So therefore, n is 32 over 64, which of course simplifies down to exactly half. So now we know that n is a half, we can substitute this in, and then we finally got our full equation. So n is a half, so x equals 1/2 z to the 6. And that's all we need to do. Let's move on now and have a look at number 18. Question 18, we have quite a tricky vector problem, so we'll get straight to it. So we've got OABC is a trapezium. So B is parallel to the base 3B, and OA and BC are two non-parallel sides of a left and right hand side. So the vectors have been labelled on for us, which is helpful to an extent, and we're then told about D being on the point from O to B, such that it splits the line O to B in a certain ratio. So OD is 2 parts and DB is 3 parts. So in other words, OD is 2/5, because 2 plus 3 is 5 parts in total, and DB is 3/5 of the total length of OB. And E, similar thing there with splitting the line BC into a ratio. Ultimately, we need to work out vector D to E from here to here in terms of A and B, giving your answer in simplest form. So there's quite a few steps to go through before we can arrive at a final answer to this one. So first of all, O to B. So let's just think about how we'd go from O to B using the vectors we know. So we could go from O to B by going from O to A, then when we're at A, we could go from A to B. So we could go from O to A, which is vector A, then from A to B, which is vector B. So simply, O to B is just A plus B. Now we can think about what it says about D being on OB, such that it splits OB in this ratio. So essentially, OD is 2/5 of the length from O to B, like I said earlier, and DB is 3/5 of the length. So let's just think about this in a bit more detail now. In other words, OD, because it's 2/5, OD is going to be 2/5 of the distance from A to B, because that's what OB is in terms of A plus B. And from D to B is 3/5 of OB, which is 3/5 of this A plus B here. So we can label on these distances now for OD and DB. Next, we need to think about from B to C. From B to C, how would we go from B to C? Well, we'd go from B to O, and then from O to C. But from B to O is like O to B, but in the opposite direction. So BO is minus vector OB. And because you know vector OB is simply A plus B, we can substitute into these brackets vector A plus B. And the vector from O to C is, of course, a 3B. And that's a bit naughty of me. I should have actually had a little vector arrow on that OC there as well. Whoops. So minus OB is minus A plus B, then plus vector OC is plus 3B. So this gives us minus A, and then 3B minus 1B gives us 2B. So this ends up being 2B minus A. I'll have to keep correcting that now, I think. So B to C is 2B minus A. However, B to C is split with this point E. So E splits B to C so that BE to EC is 1 dot dot 4. 1 part plus 4 parts is 5 parts. So that means BE is 1/5 of the length from B to C. So in other words, BE is 1/5 of this, and EC is the other 4/5 of this. So putting this into vector format, we can say that from B to E is 1/5 of BC, which we found here, and E to C is the other 4/5. So just like we did for OD and DB, we can add in these distances on our diagram as well. Now we're getting close to actually solving what we want to. We need to find vector DE in terms of A and B. So from D to E means from this point here to where it says E, using vectors we know. Well, we now know from D to B is 3/5 of A plus B. Then once we've gone from D to B, we can then go from B to E. So we've got from D to E using the blue and the green vectors. So we can actually solve the question now, because we know DB and BE in terms of A and B, so it should all fall out just fine. So from D to E, we can use DB plus BE. This is our starting point. From D to B is 3/5 A plus B, and then also we can add on 1/5 of 2B minus A. So now all we need to do is to expand these brackets. Even though there's vectors in the brackets, we just expand brackets like we normally would. So 3/5 of an A, then 1/5 times minus A will expand to give minus 1/5 of an A. 3/5 of an A minus 1/5 of an A leaves us with 2/5 of vector A. And then 3/5 of B plus 1/5 times 2B. 1/5 times 2B is 2/5 of a B, plus these 3/5 of a B give us 1 whole B in total. So we have 2a, 2/5 of an a plus b. Question 19. At the start of year n, the number of animals in a population is p subscript n. And at the start of the following year, the number of animals in the population is p subscript n plus 1, where p subscript n plus 1 equals k multiplied by p subscript n. Before I get started with actually tackling this question, I just want to talk you through what these subscripts mean, because they're actually very simple, but it confuses lots and lots of students, because it just seems so much harder than it actually is. So the first thing I'd mention is n plus 1 and n are just two consecutive numbers. So n might be 7, n plus 1 would be 8. So the next door neighbour numbers. So n plus 1 just means the number which is 1 bigger than n. That's all it means. So for example, if p subscript n meant the population in 2015, then p subscript n plus 1 would represent the population in 1 year more than 2015, in other words 2015 plus 1, which would be 2016. So the subscript n plus 1 is just the next value in the sequence of all the p subscript n's, n plus 1, n plus 2's and so on. So let's just use this formula. I'm going to put it here to one side. In 2017, the number of animals in the population was 4,000, and before I put this formula to one side, as well we're told about 2019, at the start of 2019, the number of animals in the population was 3,610. So the formula, p subscript n plus 1 equals k multiplied by pn. So what could we pick for n plus 1, and what could we pick for n? Well, what's the earliest date back we can go, the earliest year? Well, nothing's mentioned before 2017, so let's pick our n as being 2017. If our n is 2017, then n plus 1 will be 2017 plus 1, which will be 2018. So this is how we're going to set up this formula. So it's k multiplied by the population in 2017. So it's k multiplied by 4,000, because the population in 2017 was 4,000. So therefore, the population in year 2018 is k times 4,000, or I'm just going to call it 4,000k. We can now use this formula again, but go up 1 year. So instead of 2018, 2017, now I'm going to have 2019 based off 2018. So it keeps going in this same way. So the population in 2019 will be the same constant k, which we don't yet know, multiplied by the population in year 2018. The population in year 2018, we have an expression for that now in terms of k, so we can switch p subscript to 2018 with 4,000k. So the next step, we can say the population in 2019, that should say, my bad, equals k multiplied by 4,000k. Therefore, simplifying, because k times k is k squared, we then see that the population in 2019 must be 4,000 multiplied by k squared. Let's change that to a 19 because it's annoying otherwise. But we're actually told what the population in 2019 is. At the start of 2019, the number of animals in the population was 3,610. So we can just simply say that this value is 3,610, so therefore 3,610 equals 4,000k squared. So now, after all that, we've actually got a fairly simple equation to solve. Just switching this error again. My apologies, under OCD. So we can get k squared on its own by dividing both sides by 4,000. So let's do that as our first step. So divide by 4,000 on both sides. That tells us that k squared equals 3,610 divided by 4,000. That gives us a value of 361 over 400, or 0.9025, whichever you prefer. So therefore, final step, k will be the square root of this 0.9025 value. So let's see what this gives us on the calculator. So square root of the answer which has just been stored gives us 19 over 20, or we can say 0.95. So either as a decimal 0.95, that's fine, or as a fraction 19 over 20. Whichever answer you want to give is absolutely fine. Question 20. We've got Pat throwing a fair coin n times. Find an expression in terms of n for the probability that Pat gets at least one head and at least one tail when he's thrown this coin n times. Now n could be any whole number. He could be throwing it hundreds of times, thousands of times, maybe just a few. But let's just assume for now that actually he's flipped it several times at least. So n is at least 5, 6 or several anyway. So let's just think about this before we get into it. It's almost bound to happen that at some point he'd get one of each. For example, imagine he flipped a coin 100 times. I mean, how could he not get at least one of each? And that's the best way into thinking through this question. How could this not happen? How could he flip a coin several times over and not get at least one head and one tail? There's actually only two ways in which a sequence of several coin throws would not result in at least one of each. And the two ways that could happen are if either all the throws are heads or every single one of the throws are tails. That's the only two ways it can't happen where you don't get at least one head and one tail. So we can now build in the formula we need to solve by just thinking it through carefully and logically. So just taking this line a bit further, where I've said the only two ways it can't happen is if all throws are heads or all throws are tails, we could say therefore that we are certain to get one of each unless all throws are heads or all throws are tails. We can take this sentence here and build a mathematical formula from it. So, what is the chance of getting at least one head and one tail? What I said here is we're certain to get at least one of each. With this caveat here I'll come to next. What's certainty in terms of probability? On the probability scale, 0 isn't possible and 1 is certain. So when I say we are certain to get one of each, I can put here that's equal to 1. So I'm certain to get at least one head and one tail. But now I've put unless. So unless basically means apart from if something else happens. So unless or apart from means we need to subtract some value. So unless we can build in with a subtract here. Then it says all throws are heads. So how could all throws be heads? Well, that's a probability that you've got head first, head, 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 and so on and so on. So that's this one here. Or, now or, for example, what's the chance of rolling a 2 or a 3 on a dice? That's 1/6 plus 1/6. Or works as add. So we need to add in the probability that all throws are tails, which is similar to this bit here, but instead of P, H, H, H indefinitely, we're going to have P, T, 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 T indefinitely. Like so. So, we've actually pretty much got it here. So, this here, this formula, we've got 1 minus P. Now all these heads here, if the coin's been flipped n times, that would mean P, H, times P, H, all the way times P, H. So that would be if all of these n throws were heads. So that would have to be where you get n heads in a row. So I'd have to just add this in here. That's like n times of that. Or the chance of getting tails n times in a row. Chance of getting tails once, and then tails again, and then tails a third time, and so on, and so on, and so on. Put all this in brackets, of course. This again would be n times that would happen. So, 1 is obviously just 1 minus. What's the probability of landing on heads with a coin? Well, it's 50-50 if it's a fair coin. And it does say here that he's got a fair coin. So the chance of getting heads, probability of getting a head on a coin is 1/2. So that's 1 minus a half, multiplied by itself again and again. So how many times am I multiplying half by itself? To what power should I raise it? Well, if I'm multiplying pH in a string of n times, then the power will be n. So that's the probability that all throws are heads. But as well, I need to add on to that the possibility that we have n tails in a row. Chance of one tail is a half. Chance of n tails in a row is half to the power n. So then neating this up, it's simply 1 minus a half n to the power n, meaning, then minus a half to the power n for the other possibility as well. Not a very obvious question at all. I think that one's quite nasty, to be honest. Well done if you got that one. That is not straightforward. Question 1, we've got a speed time graph showing the speed in meters per second of an object t seconds after it started to move from rest. In other words, started to move from when it was stationary. Using 3 trapeziums of equal width, work out an estimate for the area under the graph between t equals 1 and t equals 4. So, trapeziums. We need to work out the area of some of these trapeziums. So the formula for the area of trapezium is as follows. It's half of a plus b multiplied by h. The way I think of this is we add together the two sides of the trapezium which are parallel, we then half that and then multiply by h, where h is the perpendicular distance between the two parallel sides. So we want 3 trapeziums in between t equals 1, t equals 2, 3 and 4. So they're going to look like this here. So if I just add a bit of colour to them so you can see them more easily, I'll have a yellow, a blue and a green one. So what we can do now is read off on here for the heights. So this one coming up at 1, that's got a height of 4. This one at time being 2 seconds has a height of 6. At the point where time is 3 seconds, read up and along, that comes to 7.2. You need to be accurate of how you read it. And finally at 4 seconds reading up and along, that's 7.8 meters per second on the y-axis. So we've got 3 separate trapeziums to work the area out of. So h, like I said, is the perpendicular distance in between the two parallel sides. So this one here, in between 1 and 2, that's a gap of 1. In between 2 and 3, the same gap. So here, h is 1 for all of these trapeziums. So because h is 1, we can get rid of h and actually replace it with multiplying by 1, because timesing by h is the same as timesing by 1. But of course, if you multiply by 1, there's no point even including that. A plus b times 1 is just best left as just a plus b. So we can also just forget the times 1 altogether. So now, thinking about these areas, the first one is going to be half 4 plus 6, because that parallel side is 4 and that one's 6. The next one is going to be half, then in brackets, 6 plus 7.2. And the final one, again, plus half. The A for the final one is 7.2, B for the final one is 7.8. So then plus half, then brackets, 7.2 multiplied by 7.8. So on the calculator now, let's just try this together. So we've got half 4 plus 6. Could do this without a calculator as well, actually, in fairness. But never mind, plus half. 6 plus 7.2. Probably best doing it on a calculator, actually. Then plus half again. Brackets 7.2 plus 7.8. Close brackets, press equals. We get 191 over 10, which is 19.1. So therefore, the total area is 19.1. What does the area represent? Well, we can sort of guesstimate this. We're multiplying basically a unit on the vertical direction by the units going horizontally. We're multiplying these units, meters per second, by these units here, which are seconds. So meters per second times seconds, whatever it is, the units of it, just with a simple dimensional analysis, the units are going to be meters. I can barely talk today for some reason. So the units are going to be meters. So because of that, and in fact what we should ideally know anyway, is the area under a speed time graph tells us the distance the object's moved. So in terms of what this area represents, 19.1 is 19.1 metres. So it represents the distance the object travels in metres between 1 second and 4 seconds of its motion. Question 22, we need to show that this can be written in this form where r is an integer. So first of all, 6x cubed, and now what we can do here, just looking at this first step, 9 and 144 are both factors of 9. So both multiples of 9, rather. So 1 plus 4 plus 4 is 9. That's the clue that 144 is divisible by 9. So first of all, I'm just going to factorise out the 9 here. 144 divided by 9 gives 16. So I've got x squared minus 16. So as a first step, just change that into this. Then just remembering from year 7s and 8s, when we've got one fraction divided by another, we can keep the first fraction, change the divide to a times sign, and flip this one on its head. And then we get 3 lots of x minus, so 2x4 on the bottom, just by flipping this on its head. So we can now neaten this up some more. So we've got one fraction multiplied by another now, so we can just multiply the tops together. So 6 multiplied by 3 gives 18, x cubed, brackets x minus 4. On the bottom, 9 times 2, I'm going to put at the front. I'll also put this x to the 4 at the front too. And then this x squared plus 16, that's actually a difference of 2 squares. X squared square rooted is x, 16 square rooted is 4. So I can switch this and replace with x plus 4, x minus 4. I need that fraction to be slightly longer now. There we go. So we can now simplify an awful lot of this. So looking at the top, x minus 4, when if divided by x minus 4, that will cancel. 18 on top, 9 times 2 on the bottom is 18 as well. So 9 times 2, that 18, will cancel with this 18. So what I'm going to have here is x cubed on top, divided by x to the 4, x plus 4. So x cubed divided by x to the 4, basically, if I think about this in terms of x as written out in the long way, x cubed, if I picture this as x times x times x, then x to the 4, if I picture this as x times x times x times x times x, just to make it easier to see where this comes from, then this x will cancel with this one, with that one, that one, with that one. So just have just for one x on the bottom. So on top everything cancels, everything divided by itself just gives 1. On the bottom I've got x, then brackets, x plus 4. Question 23. Very, very awkward, this one. So ABC is a triangle, the whole triangle like so, and D is the point on BC, such that angle BAD is angle DAC, which is x degrees. And so AD is the angle bisector of the angle BAC. This angle's been split in half, x on the left and x on the right. We need to prove that the ratio of the sides AB to BD is the same as the ratio of sides AC to DC. Now, where to start with this is by far the hardest part, and I could well forgive you, even if you go on and do very well at A-level, I can forgive you for not knowing where to start with this one. It turns out what we need to do is consider the areas of these two constituent triangles separately in 2 different ways. So, we've got these 4 sides to consider: AB, BD, AC, and DC. So if I add these onto the diagram and colour code it, like so, that's for sides, and obviously A to D is a shared side for each of these triangles as well. So now if I just think about this triangle here, ABD separately, and also triangle ADC separately too. Each triangle has an angle X in it, so angle ABD, so the angle here at A is X, and X there as well. So I've sectioned off these triangles into two separate ones like so, and now what I need to do is think of the areas of them in two separate ways. So on the left, I'm going to work out the areas using the half times base times height formula. On the right hand side, I'm going to work out the areas using the half AB sine C formula, which you should have used and been familiar with by now. So on the left, half times base times height. So I need to designate a perpendicular height for these two triangles. So what I'm going to do here, I'm just going to call the perpendicular height going straight from A, straight down to the ground at B, but in a straight line down. So if I just label this on here, then that's what I'm talking about for H, for height. So let's think about this now for triangle ABD and triangle ADC. Let's think in terms of just ABD. For triangle ABD, half times base times height is half times a base, BD, times the height, which is H. If we now think of this triangle here, ADC, then half times base times height for this one will be half times DC times H. Now if we put ABD as a fraction of the area of ADC, then we can write this and simplify much easier. So both fractions have a half on the numerator and denominator, so we can cancel the halves. Both fractions have a h on the numerator and denominator, so actually area ABD as a fraction of area ADC is BD over DC. So we can add this down. That's one area as a fraction of the other. One triangle's area as a fraction of the other. We've proven it's BD over DC. We can now prove that the fraction of this triangle as a fraction over this one is a different expression to this one, and then we can equate them. So we've done half base times height. Let's now think of the half AB sine C formula. So for triangle ABD, half AB sine C means half times one side times the other side, either side of the angle we know, then times by sine of the angle we do know. So for ABD, it's half times AB times AD times sine x. And for ADC, half AB sine C is half times AD times AC times sine x. In fact, I'm going to give it as half times AC times AD times sine x in that order instead. So it's the same fraction as what we had before, look, but now we've got it looking a bit different. So let's simplify this again. So half on top, half on the bottom, we can cancel the halves. AD and AD can cancel. Sin x and sin x will cancel as well. So we've also shown now that the area of ABD as a fraction of the area of ADC is AB over AC. But it's also equal to BD over DC as well. So therefore what we can say is BD over DC must equal AB over AC. We can then solve this by cross multiplying. And if we do that, we get BD times AC equals AB times DC. Now what we want to divide both sides by DC. Let's make some more space here as well. That triangle serve its purpose. So dividing both sides by DC, we have BD times AC over DC, and then the DC's cancel here, just leaving with us AB. Then finally, if we divide both sides now by BD, Then on the right, we have AB over BD, and over here, BD divided by BD cancels, which just leaves us with AC on the top and DC on the bottom, which is exactly what we wanted to prove. I've just been a bit silly and wrote it the wrong way round. So based off this, if I just switch the order around, I can then say that therefore AB over BD does equal AC over DC. And that, I thought, was an absolute nightmare of a question. But there you go, sometimes they are a nightmare. That's the last question done, and therefore the whole paper's been finished off. So I hope you found that useful and not too boring. I know you probably have lives and don't want to listen to these videos forever and ever, but as I say, I do hope it's useful just at some point in your life, if not for very often at all. Thank you for listening. Please do consider subscribing. I hope to hear from you soon, and please do take care of yourselves and be nice to one another.